Hello class, you're welcome again. Today we are going to study periodic properties of the elements. Electrons in atoms. When elements react to form compounds, electrons are either transferred from one atom to another, or the atoms simply share electrons among themselves. Therefore, electrons are critical in determining the properties of elements. A better understanding of electrons in atoms may help us to better understand the properties of elements. Electron spin. Experiments have shown that when electrons in atoms are not static, they are constantly spinning. They're spinning. As they spin, they generate magnetic field. It is important to study the spinning pattern of the electrons in atoms and find out how it affects the properties of elements. Properties of electron spin. Spin is a fundamental property of all electrons. We saw that in chapter 7. All electrons have the same amount of spin. The orientation of the electron spin is quantized. It can only be in one direction or its opposite direction. That is, spin up or spin down. Either it is spin up or is spin down. The spin quantum number, ms. Remember we saw it in chapter 7. Spin quantum number describes how the electron spins on its axis. Spin up or spin down. So this is hydrogen, this is spin up. This is how we represent it in a box. That's one electron where the spin is up. Spin must cancel in an orbital. So ms can have values of plus half or minus half. Pauli's exclusion principle states that no two electrons in an atom may have the same set of 4 quantum the 4 quantum numbers, we know them. In chapter 7. Principal quantum number 1, azimuthal quantum number L, which determines the shape. Then that will determine it determines the orientation, that is ml, then ms, the spin. Those are the 4. So no two electrons in an atom may have the same set of 4 quantum numbers. No two electrons. Each electron has its own. Therefore, no orbital may have more than 2 electrons. Each orbital can have only a maximum of 2 electrons, and they must have opposite spin. So let's recall. I was trying to talk about it, but let's go back again. Recall the quantum numbers. Let's remind ourselves of the quantum numbers. So these are the quantum numbers. The principal quantum number, n, can have values of 1, 2, 3. And it determines the size and energy of the orbitals. The azimuthal quantum number, L, can have values from 0, 1, 2 to n minus 1. So it determines the shape of the orbitals. We are talking about orbitals. Then the magnetic quantum number, ML, that's it, ML, can take values from minus L to plus L. So the number that we can have maximum is 2L plus 1. It determines the orientation of the orbital. Then MS, plus half, minus half, or plus half, we can have a maximum of 2. It determines the direction of electron spin. So these are the 4 quantum numbers: principal quantum number N, azimuthal quantum number L, magnetic quantum number ML, and spin quantum number MS. Quantum number of helium electrons. Helium has 2 electrons. Both electrons are in the first energy level. Both electrons are in the s orbital of the first energy level. Since they are in the same orbital, they must have opposite spin, spin up and spin down, before they can live together in that orbital. So first electron, N is 1, L is 0, ML is 0, MS is half. Second electron, N is 1, L is 0, ML is 0, MS is minus half. So those are the quantum numbers for helium electrons. So let's talk about electron configuration. The ground state of the electron is the lowest energy orbital it can occupy. The distribution of electrons into the various orbitals in an atom in its ground state is called electron configuration. I'll repeat it again. The distribution of electrons, how electrons are arranged into its orbitals in an atom in its ground state is what we call electron configuration. For instance, the electronic configuration of helium is 1s2. That's how we read it. So the number designates the principal energy level. The number, this time we are talking about the number. The number 1, this 1, designates the principal energy level in which the electron is. The letter S designates the sublevel and the type of orbital in which the electrons are. The superscript 2, this superscript here 2, designates the number of electrons in that sublevel. So that is the electron configuration for helium. We can also represent electrons as orbital diagrams. So orbital diagrams, we often represent an orbital as a square box. You see, this is a square box. This orbital is unoccupied. and the electrons in that orbital as arrows. That's how we represent an orbital diagram. The direction of the arrow represents the spin of the electron. So this is an unoccupied orbital. This orbital has one electron, and this orbital has two electrons. Spin up and spin down. Sub-level splitting in multi-electron atoms. The sublevels in each principal energy shell of hydrogen all have the same energy because it doesn't contain electrons or other single electron systems. We call orbitals with the same energy degenerate. For multi-electron atoms, the energies of the sublevel are split because they have electrons caused by electron-electron repulsion. The lower the value of the L quantum number, the less energy the sublevel has. So S is less than P, and P is less than D, and D is less than F. Orbital penetration and shielding. 2s orbital penetrate more than does the 2p. You can see them here. This is 1s, you see it here. This is 1s. This is 2p. And this is 2s. But see, 2s penetrates right inside the nucleus. That's it. 2s penetrate right inside the nucleus. This means electrons in the 2p are more shielded from the attractive force of the nucleus, the positive attractive force of the nucleus, because the protons are in the nucleus of the atom and they are positively charged. Meanwhile, the electrons are negatively charged. So electrons in the 2s are less shielded from the attractive force from the nucleus. The result is that the electrons in 2s sublevel are lower in energy than the electrons in 2p sublevel. So that's what the result of this penetration has. So we'll take, for example, look at shielding. So this is a nucleus, it has +3 charge. Then we have these 2 electrons. Then we have a third electron. This is experiencing a net charge of about +1 from this +3 because these 2 electrons are shielding it. But let's look at this electron here. This electron is experiencing a full +3 charge, this one, because it's right inside, almost very close to the nucleus. It has penetrated into the nucleus. So we want to look at how this the orbitals are likely to be arranged in a multi-electron electron atom. You see 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4. So this is a likely way of seeing how the orbitals are arranged in a multi-electron atom. If it were hydrogen, they will be degenerate. The 2s and 2p will be on the same line because they don't have electrons, and the 3s, 3p, and 3d will be on the same line because they do not carry electrons. But when they have electrons, it's slightly different. Notice, because of penetration, sublevel within an energy level are not degenerate. So penetration of the fourth and higher energy level is so strong that their n sublevels are lower in energy than these sublevels of lower energy levels. So what does this lower energy level mean? It means that when it has a lower energy, electrons enter into them before they enter into the other ones which are higher in energy. So energy difference between levels becomes smaller and for higher energy levels. Filling the orbitals with electrons. Energy shells fill from lowest energy to highest. Sublevel fill from lowest energy to highest. S, P, D, and F. We call this the off-bow principle. This off-bow principle. Let's look at another principle that controls the filling of electrons in atoms that have multi-electrons. Principle number 2, no more than 2 electrons per orbital. So each orbital can take a maximum of only 2 electrons. This is Pauli exclusion principle. Then principle number 3, when filling orbitals that have the same energy, place 1 electron in each before completing the orbitals. I'll just give you an example. We have 3 orbitals in the P. So if you have to fill electrons in these 3 p orbitals, you have to fill this first, you fill this first, then you follow by this, before you can do pairing. Each orbital must have 1 electron first before pairing can start. So you must have this. One, you put another one here, put another one here, before pairing can start. Then before you can pair. So that is how we feel it. That's Hund's rule. So let's look at electron configuration of atoms in their ground states. Let's look at some examples. I'll look at how their orbital diagrams are being drawn. Electron configuration of atoms in the ground state and their orbital diagrams. So electron configuration is the listing of electrons in subshell based on their energy. So let's look at lithium. Lithium has 3 electrons. Its electron configuration is 1s2, 2s1. So these are the electrons. And what is its orbital diagram? 1s2, 1s, you see, the orbitals are represented in a box and the electrons are represented in spin up, spin down. Then the other electron is in the next orbital, which is 2s, and is spin up. Because we cannot have 3 electrons in one orbital. So when you fill the first orbital with 2 electrons, spin up, spin down, then you move to the next orbital, which has a lower energy, and fill the next electron with spin up. Let's look at beryllium. Beryllium has 4 electrons. You have 1s2, 2s2. That's the electron configuration. Then its orbital diagram, you see, the orbitals are represented as a box, which are these 2 orbitals. 1s has 2 electrons spin up, spin down, and 2s has 2 electrons spin up, spin down. Let's take boron. This is boron. It has 5 electrons, and its electron configuration is 1s2, 2s2, 2p, 2p1. So look at this orbital diagram. You see the 2p has 1 electron. Then carbon has 6 electrons, 1s2, 2s2, 2p2. But look at this orbital diagram. The orbital diagram will not show you the electron configuration will not show you how these electrons are arranged. That's why we need the orbital diagram. The orbital diagram will show you that the electrons are unpaired. The electronic configuration will not show you that the electrons are unpaired. So that's why we draw the the orbital diagram, so that we can see the orbitals which are not filled, that need to be filled. So, order of subshell filling in ground state electron configuration. So, we want to see the order in which these electrons fill. So, drawing a diagram with each energy shell on one row. So, the way we do it, I would like to do it somewhere. So, let's take, for example, this is 1s. It has only 1 orbital. 2s has 2 subshells, but it has 4 orbital. But we are just writing the subshells. So this is n equals to 2. It has 1, 2s, and 2p. I want to show you how we write it. Then we have 3s, 3p, and 3d. I will not go right to the 5. Let's see. Then this one we have 4s, 4p, 3d, and 4d, and 4f. So if we want to fill this orbital, you're going to start with this. You fill this one first. Then you go in here, cross here. Then you start to fill this one. Sorry, let's look at it well. Oh my goodness. Okay, so let's fill it. I just want us to do it. This is 1s here. So you're filling this first. Then move in here. Then you fill this one. So when you fill this one, then you go like this. You fill 2p. Then you fill 3s. Then you go in here like this. Then now you fill 3p and 4s. Then you enter here like this. This is the arrow. Go inside here. Then you start now from 3D. Then you go down to whatever is there. Then you go now. Then you start with 4D. You see? That's it. I just want to show you so that in case you're doing it. First of all, write the orbitals down. The s orbitals down. Then the second row starts with 2p, go down. I mean the second column. So in the column 1, you write the s orbitals. Just write them down. Then the second column, write the p's down. Then now you start filling them. So that's how you're going to get the electronic configuration. So draw all diagram with each energy shell on one row. So that is it. Next, draw arrows down through the diagonals, looping back to the next diagonal each time. So you see, you write this down first. Then now you start filling S, then you go to P, to 2S, then you go to 2P, then you go to 3D, then you go to 3P, then you go to 3D down, then you go to 4D. So that's it. That's how we get the electronic configuration of elements. So let's take an example. Write the full ground state orbital diagram and electron configuration for manganese. Manganese atomic number is 25, which shows that it has 25 electrons. So let's look at, we want to write this 25 electron. So we start with S. So we are going to write 1s, 2. Then we go to 2s, 2. Then we go to 2p, 2. From 2p, so you come to 3s, 2. From 3s, you go back to 3p. Oh, this is 6. 6. Then we go to 4s, 2. Then we go to 3D, 10. Then we go to 4p, 6. So we need to get 25 electrons. I've been writing, I don't even know where I've ended. Let's see. So we have 4, 10. We have 20. So here, we want 25 electrons. So here, we will have bed 5. So that is a ground state electronic configuration for manganese. You follow this method to write. So you see we're ending in D. 1s, 2, 2s, 2, 2p can have a maximum of 6 electrons, 6. 3s2, 3p, 6, 4s, 2, then 3d. 3d, because we have 25 electrons, it contains 5 electrons. And if we have to write the orbital diagram of 3d, just write it. D has 5 orbitals. 1, 2, 3, 4, 5. Each will have electron spin up, because we have to put 1 electron in each before pairing. So that is how the electrons will look like in this 3D orbital. So based on the order of subshell filling, we will need the first 7 subshells. 1, 2, 3, 4, 5, 6, 7. So these are the 7 subshells. One S, 2S, 2P, 3S, 3P4 in this order, and 3D. It must be in this order. Then we start filling the electrons. So those are the electrons which have been filled. So our electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5 based on our rule. Let's try this example also. So write the full ground state electronic configuration for potassium. Let's try this. Potassium. What's the atomic number of potassium? So go to your periodic table. Atomic number of potassium, I have it as 19. It means it has 19 electrons. So based on our diagram, how do we fill the electron? We have to fill it and counting it. So 1s2, 2s2, 2p6, 3s2, we have used how many? 10 already, 12, 3s2, 3p6, 4s1, 1, 2, 3, 4, 5, 6. So here we have 10, 19. So this is the ground state electronic configuration for potassium. So try and practice. I'll give you another one. Write the ground state electronic configuration for gallium. I'll give you another question. So write for this. Write the ground electronic configuration for gallium and selenium. Do it as practice at home. So we'll stop here for now. We'll continue. Please make sure you do your homework. Try to practice to write the electronic configuration for gallium and selenium. Okay, we'll continue from there.